Hello, and thank you for visiting our poster. My name is Julie Younes, and I'm a PhD candidate under the supervision of Professor Giovanni Grasselli at the University of Toronto in civil engineering with a focus on geomechanics. Today, I'd like to talk about the geomechanical behavior of salt under rapid cycling, specifically in the context of hydrogen storage, through our work on the YH2J vessel. To meet the emission reduction targets of the Paris Agreement and decrease dependency on fossil fuels, renewable energy sources like wind and solar, although intermittent, are essential. And with the growing global demand for energy, many countries are also focusing on energy security, subsequently increasing the importance of energy storage. Salt caverns specifically are widely used for large-scale energy storage, including natural gas, hydrogen, and compressed air due to salt's low permeability and self-healing properties. And when a cavern is constructed, the surrounding salt undergoes changes, resulting in a narrow zone of damaged rock, known as the excavation damage zone. The deformation in this area can increase significantly due to the impact of pressure fluctuations during operation, and therefore a competition arises between the increase in damage and the healing effect in the surrounding salt. And although healing reduces leakage, its rate depends on stress, temperature, impurities, and the excavation geometry. Since caverns undergo cyclic loading, incomplete or delayed healing can lead to crack growth, increased permeability, and potential loss of containment. So, quantifying and optimizing the healing process is therefore critical for the long-term stability, safety, and efficiency of salt-based energy storage systems. The nature of crack self-healing in salt involves three distinct physical mechanisms. Namely, the one we will focus on is the pressure closure, where the microcracks are closed under pressure and the two surfaces of the cracks contact with each other and form a chain network by bonding. Salt's ability to recover the mechanical strength and integrity through healing is less understood. So to address this, we combined mechanical testing with high-resolution X-ray computed tomography to visualize and quantify the internal crack closure and healing progression in real time, as understanding the self-healing behavior is essential for improving cavern stability, extending service life, and ensuring safe operations. So we designed and developed in-house a custom X-ray transparent vessel, inspired and adapted from previous designs, introduced in literature as a starting point. The YH2J vessel will enable in situ micro CT imaging during stage loading and healing sequences. By leveraging prior work on pressure cells for X-ray based measurements, we incorporated elements to allow for multi-processes experiments. So we created a pressure cell that can withstand high pressures, both radially and axially. And the material used will be able to withstand extreme temperatures without obstructing the X-ray signal. We also incorporated ultrasonic piezo sensors into the platens, which also added another layer of complexity, but will provide invaluable insights into the material properties of salt under stress. And also, we accounted for fluid flow, so we incorporated fluid channels to simulate real-world conditions, such as those found in underground storage caverns. Now, in parallel, an initial baseline study began with a scan immediately after specimen preparation, followed by a healing period under controlled conditions. The specimen was then mechanically loaded, while a digital image correlation system monitored full field surface strains and fracture development. Now, after loading, the sample was allowed to heal under the same conditions and rescanned multiple times to track crack closure. The internal damage was assessed from the CT scanning data, which used the grayscale images, first adjusted and corrected to reconstruct the 3D volume, then to obtain the microstructural information The voxels in the CT images were classified to distinguish between fractures and the salt matrix and create the segmented volume. And then finally, the specimens underwent a second cycle of loading to assess the residual strength and healing effectiveness. The preliminary test showed through micro CT scans that the cracks did not fully close, although some reduction in the aperture was observed. We also observed a clear degradation of mechanical strength after healing. So we were able to see a lower peak stress, reduced strain capacity, and an earlier softening compared to the first cycle of loading. This indicated only partial recovery of mechanical strength and ductility. And in the second cycle of loading, the crack opening occurred earlier and at a lower load level, which was consistent with the CT results, showing that although the crack was significantly reduced in size by healing, it did not fully close. And upon retesting, the crack aperture widened substantially, confirming that healing improved but did not restore the original structure integrity of the samples. Thus, there was an incomplete recovery under the rapid cycles, which may pose challenges for long-term cavern stability. The upcoming development of the YH2J vessel will enable more detailed real-time investigation of healing under the operationally relevant conditions, ultimately improving hydrogen storage, the safety and efficiency, highlighting the importance of observing and quantifying the optimal healing time to maximize recovery. And with that, I would like to thank you for your attention. I'm happy to discuss any questions or details, so if you have any questions, please make sure to reach out. Thank you.